In this video, we're going to have a look at calculus for the context of physics. We're going to look at slope, area, that is derivatives and integrals, understanding them in the context of kinematic equations today on High Peak Education. Hello and what is going on, everybody? Hope you're having just a great day, and thank you for your support of this channel. So, we're taking a look at calculus as it relates to physics. We're going to look at how secant lines become tangent lines. That is, average rate of change becomes instantaneous rate of change. We're going to compare functions to their derivatives and integrals. We're going to look at motion diagrams. We're going to look at position versus time, velocity versus time, acceleration versus time graphs plotted simultaneously for a simulated car that's moving. And we're going to look at how the variables and the equations go together on those x versus t, v versus t, and a versus t diagrams. We'll be talking a lot today about slopes of various graphs and then area between the curve and the horizontal time axis of various graphs. So that'll give us the notion of derivatives and integrals. Without any further delay, let's get into today's content. So let's get started with calculus as it relates to calculus that you need to understand physics. And specifically in this video, we'll be taking a look at calculus as it relates to linear motion. So let's start off here with the notion of what we mean by a rate of change, and we mean by the derivative, that is the instantaneous rate of change, which we often define in calculus. Suppose we have a function which is given by this brown golden curve. And suppose you could think about this as, say, the position versus time of some particle. You could suppose the horizontal axis here is the time axis, but that's not necessarily required. In fact, if you want to call this vertical axis y and this horizontal axis x, this argument I'm about to make is also entirely true. Now notice, point A and point B are 2 points that are separated by different points along the horizontal axis. In physics, this would often be time A and time B. Notice that between points A and B, we calculate the slope, and that's going to be the change in the vertical axis variable divided by the change in the horizontal axis variable. So in math class, you'd often do change in y over change in x. In physics, if this is position on the vertical axis versus time, it'd be change in x over change in time. However it's calculated, this would be the secant line slope. Secant line hits the curve at 2 different points, and it gives us the notion of the average rate of change. So AB has a certain slope, and it looks like it's calculated for us there. It looks like it's calculated as 2.20. Now again, if this was physics, that would be 2.20 meters per second, whereas in calculus class, you would just not put any units on it. How about point A? What is the slope at just point A? Well, at just point A, you might be interested in how fast is the object moving at just point A. That would be the change in the position over the change in time at only one moment. So in order to get the velocity, which is the slope of the position versus time graph at just one moment, what we do is we take the secant line slope and we allow this point to approach the other point. Notice that the secant line slope is now getting closer to the slope of the green line, which is the tangent slope at point A. That is tangent to the curve. And in fact, if I allow A and B to get really close to one another, such that they're basically on top of one another, the slope of the tangent line and the slope of the secant line are exactly the same. So if the points A and B are not separated in time at all, the velocity is no longer an average velocity, it's an instantaneous velocity. And that is what we mean
by the instantaneous rate of change, or in calculus we say the derivative. So we say the derivative is the slope of the tangent line to the curve at any point of interest. So in the same way, this can be a function. The derivative itself can also be a function. It can be a function of the horizontal axis variable, which is often the independent variable. Now again, in physics, position is often as a function of time. So x is a function of t. Whereas in calculus, we often say y is a function of x, or you could say f is a function of x. Either way, the idea is that, we're taking and evaluating the derivative at some point of interest. A new curve, that is a new function generated, the derivative function, but again, the geometric interpretation is the slope of the tangent line to the curve at any point of interest. So with that framework in mind, now let's look a little more deeply into calculus in terms of how we start with a function. What does its derivative function corresponding look like? And what does its definite integral function corresponding look like? So now let us get started with the calculus more formally. And now here we have a function of x, that's this function here in blue, on the vertical axis, and we have a horizontal axis that is the independent variable x. Notice also we have the integral shown here, and then we also have the derivative shown here. Now previously I've already discussed the derivative in this video, but what is the integral geometric interpretation? Is the area between the curve and the horizontal axis, and it's a signed area, S-I-G-N-E-D, signed. That is, if the function is going to be above the x-axis and it has a positive area, then the function up here has a positive vertical axis value, whereas if it's a negatively signed area, then that will be a negatively signed vertical axis value for the integral. How about the derivative? Again, it's going to have the corresponding slope of the original function for each point of interest, and we're just going to actually plot that as an actual function. So let's look at several sample functions here. The first one I'm going to start off with is a hill. So I'm going to produce a hill here, and let's see what we mean by the original function and the integral and the derivative. So let's have a look here. Here is this hill, and it looks like as we go up this hill on one side, it looks like the slope is positive over here. And notice that df dx is positive. It looks like the slope is greatest probably somewhere around here, and that corresponds to the greatest value of the derivative. But notice then the derivative quickly goes from positive to 0, and notice now here the derivative is 0, and then the slope goes to negative, so then the derivative goes to negative. It's still negative slope over here, but kind of a very gentle negative slope, so we get to a small negative derivative. How about the integral? The integral, notice that when you take the integral, notice that the integral keeps getting larger. Why is that? Well, as we go along x, we accumulate more and more area. So if I only integrate from here to here, I only have a little bit of positive area. If I integrate from here to here, I have more positive area. And notice that the area is going up the most rapidly as this function is very tall. So that's kind of the idea. And notice that the integral levels out to horizontal. Why is that? Because as we have more and more area under this curve, the function gets more area, but this area is actually pretty small. So again, it levels out because at this point, we're essentially getting the function to be near 0 again, so we're not gaining any more area, so this flattens out. Okay, think about these things in terms of how function is related to derivative and integral. Let's try another example. And then now let me try like a line, sort of triangular shape. We go from zero slope to some slope, and there's a huge spike in the derivative. But then it's constant, because the slope here is constant. And then all of a sudden we have another spike, which is a change from a positive derivative to a negative derivative. So suddenly, whew, the derivative spikes way down, and then the slope is negative, so then the function here is negative. That is, this function is the derivative function is actually negative, but it's constant. Okay, and then we go back to 0, so then the derivative is 0, and that's because we have 0 slope as well. Notice, what about the area? The area, it's growing at a quadratic rate. As we get greater and greater right triangles, if you will, summed up starting over here, we get more and more area. And then we're still getting more area as we get right triangles over here, but now the right triangles are getting smaller, so we still get more area, and then it levels off as we're not getting any more area. Let's have a look at another one. Now let's look at a parabola. So let me do a parabola that is somewhat small, that I can keep the integral on there. But notice that there's a huge derivative here that begins and ends. So I'm going to use the smooth function here. And then now we have a more sort of reasonable parabola. Now let's think about what's going on. It looks like the slope is increasing. So it's going from 0 to positive, and it's getting more and more positive, but then at about this point, I think the slope is greatest. Now that corresponds to the derivative getting larger and larger, but at this point, the positive slope is greatest. And then it's still positive, but becomes a little less, and then we get to 0 slope. So that corresponds to 0 for this derivative value. And then it's just the reverse on the other side. We become negative derivative, so we go into negative values for derivative. The slope is negative and largest magnitude here, about middle of this parabola. And then we go down to this side, it's still negative slope, but less of a slope, and there we go. This integral is hopefully what you'd expect, that when we integrate on this side, we're increasing the integral. When we get to this point, this is when the integral is actually gaining the most area, kind of in this region. And then we're still gaining area, but we go to the right, then we're getting less and less. So there you go. Let's try something else. Let's try a pedestal, which is kind of like a, sometimes called a hat or a rectangular pulse. So look at that. This rectangular pulse has infinite positive derivative on the one side and an infinite negative derivative on the other side. But notice the area under the curve is very easy to calculate, because you could just make a right triangle out of that up to a certain point. Now, of course, unless it's like a pulse that's very, very short-lived, like maybe a pulse from a laser or a pulse from an electronic device, then these kind of pulses aren't so useful. Now, even real pulses have a small amount of time where it ramps up and then goes constant, and then a small amount of time where it goes down. But let's see what happens when I smooth this out. Notice that the derivative is no longer infinite. So notice that we've got an increase in the slope here. That is, we go from 0 slope to positive slope, and then 0 slope here. The derivative is also 0 because we have 0 slope here. And then on this side, the slope is negative, so the derivative is constantly negative down here. It actually goes below the figure, so I could show it to you like that. So I zoomed out, so now you can see it a little better. How about the integral? Well, notice that it's sort of quadratic on one side. That's because we're getting right triangles here. Notice that the gaining of integral, that is area, is constant during this period of time because it's a small rectangle. But then again, we gain more area under the curve, but we gain it at sort of less and less of a rate And then so that way it sort of concave down over here. Let's look at something even a little more interesting. Let's look at a sine curve that is some sort of a oscillatory function. Wow, look at that. Okay, so notice a couple things here. First of all, notice that this function to me looks like a function that's like a sine or a cosine. In fact, let me see if I can shift this. Well, I can shift it up or down, but I can't shift it side to side. So there it is. Now notice this sine function seems to go, when it's positive derivative, that is positive slope, the function here is positive. At the top of this wave, when we're at zero slope, then we have zero derivative value. Negative slope, negative values of the derivative. And then again, zero slope, we get to zero derivative right there. How about the area under the curve? Well, the area under the curve is going to be related to just the other way around. This is a positive area, this is a negative area. This is a positive area, this is a negative area. In fact, one thing that's interesting is that this positive area will become most to this point. Do you see that point right there? That's because we're only integrating this lobe. And then how about this lobe? Well, this lobe right here is a negative area. So this negative area over time sort of cancels out this positive area, and then we get down to about zero. Okay, so that's the idea. So notice that if this is like a sine function, its derivative is like a cosine function. And if you take the integral of the sine function, you get the negative cosine function. So this is like the negative cosine function, which is, as you know, your friend, familiar cosine, but just horizontal axis reflection. Okay, I hope this all kind of makes sense. Again, this is what you should think about when you think about derivatives and integrals, the interpretation of slope and the interpretation of area. But now let's go a little further and let's start to apply this to motion. So what I have shown here is a race car for which we can control the initial velocity and the acceleration. And notice that we have no control of the initial position, so to say. Notice that if we just start, the race car is starting at negative 20 meters, and that's its initial position. Note the center of the race car is at negative 20 meters on this horizontal x-axis. And notice the velocity stays to be zero, the acceleration stays to be zero as well, as a function of time. Note x is in meters, velocity is in meters per second, acceleration is in meters per second squared. So that is to say, the function here has zero slope, and the area under the curve is most well defined if you're looking at the area under the velocity versus time graph or the acceleration versus time graph. So those would be our integrals. But let's do something a little more interesting. Let's give this car an initial velocity, and notice that it's still starting at negative 20 meters for its initial position, but now it has a positive slope, so the derivative is positive. The velocity is a constant function. That is to say, the constant slope for the derivative produces a constant function for the velocity as a function of time. When we start this, notice that the car just proceeds at a nice constant velocity. The velocity vector stays constant. And notice that, what about the area under the curve? Well, the area under the curve is best defined as the area under the velocity versus time graph, and that's going to be the displacement of the car as it moves along. Okay, so that's the basic idea. The integral here is going to be thought of as the area under the velocity versus time graph. And then now let's go something a little more interesting. Let's give it zero initial velocity, but let's give it an acceleration of 1 meter per second squared. Notice that the acceleration is constant at 1 meter per second squared. The velocity has a sloping up of 1 meter per second gained each second. And then look at the position. It's quadratic. So notice that the area under the acceleration versus time graph is going to be the velocity. That is to say, the greater and greater areas that you take, the larger and the larger velocity the car is moving. Furthermore, the acceleration is shown as a purple vector, but then the velocity vector, you'll see that's the red, will increase with time. What about the area under the velocity versus time graph? Well, that will be the position value that the car moves towards, and that'll be the net displacement. What about derivatives? Well, the slope of the position versus time graph will be the velocity, which, note that at first it's 0, but then it gets larger slope, and even larger slope, so the velocity is getting greater. And the slope of the velocity versus time graph, that's the derivative, remember, is the acceleration, and that's going to be constant and positive. So let's give this a shot. Notice that over time, the car goes faster and faster because it has a constant acceleration and its velocity is increasing. That is to say, we know the derivative of x with respect to t is v, and we know the derivative of v with respect to t is a. And we know the definite integral of a with respect to t is v, and the definite integral of v with respect to t is x. Let's keep that same acceleration, but let's increase the initial velocity. Notice what's happening. The acceleration is not changing, but that means there's going to be no change to the integral, to the area under the acceleration versus time graph, so the velocity will be the same increase, the same delta v, that is change in velocity. But look at the position versus time graph. Did you see that the position versus time graph, the slope is now greater? That's because it starts off with an initial velocity, and it also continues to increase that velocity due to the acceleration. The area under the velocity versus time graph will be larger. That is to say, the car has a greater displacement in less time. So let's go ahead and start this up. And indeed, this is what we observe. The car is moving fast, but it's also speeding up. And this is what we mean by using calculus to help us define one-dimensional linear motion. How about if it's something even more interesting, I hope? Let's give the car an initial velocity, but let's make the acceleration negative. Okay, so let's give it an acceleration of -1 meter per second squared. So that means the car should move to the right, it should slow down, and then after however many seconds, it should start moving to the left. How do we know that? Because negative acceleration means when the acceleration's in the opposite direction of the velocity, we slow down. And here we get to 0 velocity, which means the car should stop. And that will be the place where we reach the maximum position to the right of the car. Spoken in terms of calculus, we have positive derivative, 0 derivative, negative derivative. The car is moving to the right, the car is stopped, and then the car moves to the left. And then what about this derivative of the velocity versus time graph? Well, it's always negative, so that means it's always negative acceleration the entire time. So what about the integrals? The integral of this is a negative delta v, because it's negative area between the curve and the axis. So the delta v is negative, the velocity becomes more negative. And then this is positive area, that is, the car is moving to the right. And then this is negative area under the velocity versus time graph. The car is moving to the left. So have a look at this. The car is moving to the right but slowing down. Its velocity is decreasing. And now the car is moving to the left. The velocity is getting more and more negative. The speed is increasing. So hopefully you now with calculus understand one-dimensional linear motion along a line. Let's go even a little further with this with our next simulation. So now what we have shown here is an example car that's going to move to the right, to the left, on an x-axis. In fact, we should be able to predict its motion before it even occurs. Notice the derivative is positive at first, the car should move to the right, then it should stop because the derivative is 0. Then the car should move to the left because the derivative is negative. The car should be moving fastest at point D, that is 30 seconds, but then it looks like it should slow down to a stop at point F because the derivative becomes 0 again. So the car moves to the right, it slows down to a stop, it then moves to the left, retracing its steps, and then it's moving fastest at point D and stops at point F. Notice that the car starts at about 30 meters. Between points C and D, it goes past 30 meters. Notice that the starting line, which is sort of like the x equals 0 position that we choose, is shown to be here at point D when it's actually moving the fastest. But then it actually moves into negative x values, and that's just saying its position is to the left of the x-axis 0 mark that we chose. And notice that the car slows down again past this 0 mark because the derivative is smaller magnitude but still negative. So it's moving left, but it has a smaller speed. So let's show one more time. Notice the strobes are showing you where the car was at the various times: A, B, C, then D, then E, then F. So now from graphs and from actual, we would call these motion diagrams, we can actually figure out where a car is and predict its motion. All right, so let's look at just one more example, and this time it's mostly definitions. Definitions of the variables that we've been talking about and seeing them shown on a graph. That is position versus time, velocity versus time, and acceleration versus time graph, and showing the variables on there. So the last thing I want to show is some definitions of what we've been already saying. Look at the position versus time graph. That's x versus t. Remember, position, velocity, and acceleration are going to be on vertical axes, and then time is going to be on horizontal axes when we examine kinematics in physics. So notice that, look at this initial slope. This initial slope is the vxi. That's the initial x velocity. Notice that the initial position is xi. Notice up here at some later time t, then we have vxf. That's the velocity at some final time, and that final time t is the time of interest sometime later, and the slope, that is the derivative of this curve, gives us the velocity at that moment. That's the instantaneous velocity at time t, the final time. If you look at the velocity versus time graph, looks like the slope of this graph is the acceleration. Now remember, so far we've only been dealing with constant accelerations. So the velocity should be a constant slope when it is sloped on the velocity versus time graph. Its initial vertical axis value, now again, don't call it a y-intercept, call it an initial vertical axis value or vertical axis intercept if you like. That's vxi, that's the initial x velocity. Notice that its final velocity at time t is vxf, that's its final x velocity. Notice that it's vxi, that's right here, plus ax times t. Now think about this. That's how much velocity this thing gains. Why is that? Well, first of all, because it accelerates over some period of time, there's a delta t, and then it gains velocity. But another way to think about this is that ax times t is the area of some rectangle. So if you think about the integral of the acceleration versus time graph, that's going to give you some increase delta v of the velocity getting to the final velocity. Notice that, what about the area under the velocity versus time graph? Well, the area under the velocity versus time graph looks to me like a right triangle. And notice that if we're at some small time, it's a small right triangle, we haven't increased the position very much. But if we go to a larger time and we have a larger right triangle, the position has increased even further, so it's going up quadratically. And then here at the final time, that's the total displacement from xi to xf, x final. Lastly, what about the acceleration versus time graph? Remember, the acceleration versus time graphs are either 0 or they're just constant functions. So the slope is 0 and the acceleration is a nice constant function. And remember, the derivative of the velocity versus time graph is the value, the vertical axis value of the acceleration versus time that it stays constant at. Now the interesting thing is this. You see all these definitions, but prepare, the one thing that's dynamic on this little simulation is I can click on the hand and move the acceleration up and down. So notice that if I move the acceleration down, look what happens. The slope is less in the velocity versus time graph. There's less what? Concavity of the position versus time graph. It doesn't curve up as much. But if I increase the acceleration to a pretty large value, notice that the slope of the velocity versus time graph is greater slope, and the concavity, again, this is positive concavity because it's positive acceleration, of the position versus time graph is also greater. So hopefully from that, you can now understand how calculus relates to physics, especially in one-dimensional motion situations.
So what we saw in this video were several examples of using slope and integrals, that is derivatives and area. So the idea is that calculus is very important, especially if you're taking a calculus-based physics class. Now, those of you that are not in calculus-based physics but algebra-based physics, I'm sure your teacher will still use the terms slope and area, but they really mean derivative and integral, which are the calculus terms. And it turns out these are really important as it relates to the kinematic equations and understanding how shapes are made in terms of these x versus t, v versus t, a versus t graphs, and all the things that we've discussed. So hopefully by watching this, you now understand motion very well, especially from the mathematical perspective in physics. So thank you for watching High Peak Education. Let us know in the comments what other videos you want to see. Let us know how you're going to use this information in your class and in your life. Please smash that like button if you enjoy this content. Please share this video amongst your social networks. Our social media links are down in the description below. Please support us on Patreon, and we thank you for your support, and we look forward to seeing you in the next video.